Jai Hind all. Myself Amita Asthana from Ajay Kumar Garg Engineering College, Ghaziabad. Myself working as assistant professor in AKGEC in EC department. So in today's lecture, we have taken the topic of asynchronous counter from third unit of digital system design, code being KEC 302. Now, first of all, we should understand the counters. So as the name suggests, the counters are to count. Okay, maybe up counter like 0, 1, 2, 3, 4 up to whatever point we want to count, and down counter to count from reverse direction like 10, 9, 8 and so on. So here in this video lecture, since we are interested in asynchronous counter, so we need to understand what is the term which is known as asynchronous counters. The counters are the circuits, the digital circuits which are counting digitally the up and down mode. There are two types of counters. First is asynchronous counter and second one is synchronous counter. So let us understand the difference between the two. So here in asynchronous counter and synchronous counter, one basic difference is that the synchronous counters are governed by simple single clock. That means all the flip-flops used in constructing the counters, they are governed by a single clock pulse. That's the mean. That means all the flip-flops will be triggered by single clock pulse, right? Whereas in the asynchronous counter, one flip-flop is connected to another flip-flop is connected to the next, and the next flip-flop is connected to some other flip-flop, and previous output flip-flop is given input to the clock pulse of the next flip-flop. That means if I want to make a asynchronous counter, like let's say I am using two flip-flops. So let's say this is a flip-flop, T flip-flop. Okay, this is the output. Again, this is a T flip-flop, this is the output. So what I am saying is the output of the flip-flop is connected to this one. Whereas in the case of synchronous counter, the two clocks are connected to single clock pulse, right? So here one output is given as input to the next flip-flop, whereas same clock pulse is given to this one and also this one. So this is synchronous and it is asynchronous. So the basic difference is one is driving the another in case of asynchronous counter, and in the case of synchronous counter, a single clock pulse is governing all the flip-flops. So in asynchronous counter, the flip-flops are not clocked simultaneously, whereas in synchronous counter, the flip-flops are clocked simultaneously. Another thing is, since one flip-flop is governing the other, that means other to work, it has to wait for the trigger from the previous one. So that means if a sync flip flop is given to the another as input to the clock triggering, then another has to wait. If another is waiting, then obviously in case of asynchronous there would be some delay, and they will be led to a comparatively slower circuit. In the case of synchronous counter, what we are doing is we are clocking all the flip-flops with a single clock pulse, and all the flip-flops are triggered simultaneously and the circuit becomes little bit faster. This is the basic difference between the asynchronous counter and the synchronous counter. So the delay is more in case of asynchronous and delay is very less in case of synchronous counter, right. So coming to the next part, so that is let us design some counters using flip flops in which the one flip flop is triggered by some previous stage flip flop. Now the counters, as I told, it can count in upward direction, it can count in downward direction. If it counts in a up manner, then it will count as 0, 1, 2, 3 and so on. And downward direction, it will start from the highest number and then it will go to 0, right. This is a down counter. Now coming to the modulus of the counter, this is very important term and most of the students do mistakes in understanding this modulus of the counter is nothing but a very simple concept, that the modulus of the counter, which here it is written as modulus of the counter, right. So modulus of the counter is nothing but the number of states it is passing through, that's it. So number of states, that means if I want to count from 0 to 3, then the counter will count 0, then it will count 1, then it will count 2 and then it will count 3. So there are 4 states, and for such counter the modulus will be 4. So modulus is nothing but the number of states, that's it. Okay, if a counter is starting from 0, then the first state of 0 will also be a count. So here we have understood a very important concept of number of states is equal to modulus of the counter. Now each of the counts of the counter, like I said, including 0, the count 1 is also a state of the counter, the count 2 is also a state of the counter, the count 3 is also the state of the counter, and all the 4 states are important and they are individually ranked as the state of a counter. Let's say my counter is counting from 1 to 2, that means it is switching state from state 1 to state 2. So in each of the counts of the counter is called a state of the counter. In other words, the number of input pulses that causes the counter to reset to its initial count is the modulus of the counter. Since a 2-bit counter can have 4 states, for an example, like it will count 0 0, 0 1, 1 0 and 1 1. So 1 2 3 4. So a counter of 2-bit will have 4 states. The counter of 2 bits will have 4 states and modulus of the counter will be modulus 4, right? Since a 2-bit counter has 4 states and it is known as mod 4 counter. I think it is now clear to this thing. One important slide, and in which I can summarize the number of states through which the counter passes before returning to the starting state is called the modulus of the counter, and hence the modulus of the counter is equal to the total number of distinct states including 0 that a counter can store. As I made you understand that the number of states are nothing but the modulus of the counter including 0 state. Now, after understanding the asynchronous counters, the synchronous counters, their difference, let us design the counters in the asynchronous category. Now, one more important point at this particular stage, I can mention that asynchronous counter are also known as ripple counter, right? So, asynchronous counter and ripple counters are the same. So, let us design a 2-bit asynchronous counter. 2-bit asynchronous counter using JK flip flop, right? Using JK flip flop, the 2-bit ripple up counter. We are designing one up counter using negative edge triggered flip flop. So, in this diagram we can see that we have taken 2 JK flip flop, first, second. This is also JK flip flop. I have mentioned it J1, K1, Q1, Q1 bar, J2, K2, Q2. This is the negative edge triggered clock. Okay. For up counting, we have connected this Q1 to the clock of the next flip flop. So, what we are doing is we have connected this Q1 to my clock pulse of the another flip flop. So, it is a ripple counter, and this process we know as the for negative edge triggered. If it was positive edge triggered, then the connection would be different, but since it is a negative edge triggered counter, I will connect my Q1 to the next flip flop, right. So, Q1 to be connected to the next uh, clock pulse for the next flip flop, right. Now, this is how the circuit has been connected. The first flip flop, the second flip flop, their clock, it has a separate clock, and the clock to the second flip flop has been given by output of the first flip flop, right. Okay. Now, 2-bit ripple up counter using negative edge triggered flip flop. Let us understand how it works, how it is working. So, this clock I have taken as negative edge trigger. Right. Okay. Let us assume initially the output of the Q2 flip-flops were 0. The flip-flops initially I have taken as reset flip-flops, right. So what I can do is, initially the output was first flip-flop Q1 was 0. As negative edge comes, since I have given J1 and K1 to be 1, there will be a toggle from the JK flip-flop truth table. There will be a toggle at the first negative edge of the clock pulse. So, here the output will change from 0 to 1, right. Again at the negative edge this output will again get changed, and every time whenever it receives a the negative edge, it will change. So 0 then 1, 0 then 1, 0 then 1 and 0, right. This is the output for the first flip flop. It is very simple. The output will be of the first flip flop will go like this, and then this output will be fed to the second flip flop to the negative edge triggered circuit. Okay. So coming to this thing, what we have obtained is, for every negative edge, this Q1 will become clock to the next flip flop, right. This Q1 will become clock to the next flip flop, and then initially the next flip flop was at 0. So what will happen? This was 0. At this point it will change. Again at this point it will change, and again this will. So here if I write, this was 0, this was 0, this is 1, this is 1, this is 0, this is 0, and then this is 1, right. So this is my output Q2, and the same output I am predicting by the characteristics of the flip flops. The J1, the Q1, Q2 flip flops, both outputs have been drawn and they are well represented at in the figure. Now you must be analyzing where is the count. So the count is Q1, Q2. So the count is, it was initially both were 0. Okay, so this is the count, first count, then 0 1, okay, then 1 0, then 1 1, isn't it? 0 0, 0 1, 1 0. This is the count from 0, 1, 2 and 3, and hence I have made the asynchronous flip flop by using just 2 flip flops. Second flip flop clock is connected to the first flip flop output, and the waveforms clearly indicates the counting, and this is keep on counting 0 0 0 1 1 0 1 1 and so on, right. So this is how my asynchronous counter is working. Now 2-bit ripple down counter using negative edge triggered flip flop. So negative edge triggered flip flop, let's say as I have explained, this is the counting, that is Q2, Q1, like this is 0, 0, 1, 1, 0 and 1, 1. That means I have taken two flip-flops. First is J1, K1 and second one is J2, K2. And by this simple circuit which I have explained in this diagram, these are the clock pulses, and every negative edge triggering I have a change of 0 to 1 and 1 to 0, 0 to 1 and 1 to 0, as I have drawn here in this particular diagram. So this was the asynchronous counter. One important thing which we can have here, see, the main important point which we need to remember every time, this, if this is a negative edge triggered, I am connecting this Q1 to my negative edge triggering. I am connecting this Q1 to my negative edge triggering. Let's say if I want to make it work as a down counter, like starting from 0, initially both the flip flop at 0 level initially reset, and then I want to count at 0, 3, 2, 1 like this. Then what I will do, a slight change in the concept, and that will be, I will connect my Q1 bar to this negative edge triggering. So what I will do is, I will connect my negative output to the clock pulse to the next flip flop, and obviously since it is a negative edge triggering, then all the changes from 0 to 1 and 1 to 0, 0 to 1, that will happen only at the negative edge triggered. And this Q1, if this is the Q1, then it will be the Q1 bar. This is the Q1 bar. If it is 1, I have made it 0. If it is 0, I have made it 1. If it is 1, then I have made it 0. If it is 0, then it has been made to be 1. Now mention the negative edge points. Mention the negative edge points, and in the negative edge points, at each negative there will be again a switching. Why switching? There is one important question, why at every negative edge we are getting a switch from 0 to 1 and 1 to 0? Because we are putting our flip flops, JK flip flop, these both flip flops, we are giving one input, and J equal to K equal to 1, that toggles for every clock pulse, and that's why toggling, that means 0 to 1 and 1 to 0. So there is a toggle for each and every JK flip flop. We have studied the up counter and we have studied the down counter. Both the counters we have studied. Now what I want is, I want my another counter which can count up also and which can count in the down manner also. So up counter and down counter. Let us understand this thing. I want to combine these two. This flip flop arrangement and these flip flop arrangements, I need to combine both of them. So what I can do is, I want one time to work this Q1 to be connected to this negative clock pulse, and at the another time I want this Q1 bar to be connected to the next clock pulse. So what I want to do is, I will take one input, more input, one additional input I am taking. So one additional input I am taking, and that is M. Let us suppose if M is equal to 0, if M is equal to 0, and if here through this AND gate this will go 1 and this will be 0, this output will be 0 and this output will be Q1 bar. So my Q1 bar is connected to the next flip flop, and if it is Q1 bar is connected to the next flip flop, it will work as down counter. Simple. It will work as down counter. If my Q1 bar is connected to the triggering, then it will work as down counter. Another point, what I want is, if my M is 1, then this will be Q1 and this will be 0. Okay. Then my Q1 will be connected to the negative as triggered, and if Q1 is connected to the negative as triggered to the next flip flop, the counter will work as up counter. So in conclusion, I can write clock signal of flip flop 2 will be Q1 into up plus Q1 bar into down, Q1 M plus Q1 bar M bar, right. So in this way, by using 2 AND gates and 1 OR gate, I can design one asynchronous counter which can count in upward direction as well as it can count in downward direction. Only important point which I want to take is, I need to operate both the flip flops in toggle mode. First flip flop to be in toggle mode, second flip flop to be in toggle mode, and both the flip flops will toggle from 0 to 1 and 1 to 0, and this toggling property of JK flip flop and T flip flop can be used to design asynchronous counters or ripple counters very easily. So here we have seen the designing of the asynchronous counter both in upward manner and both in downward manner. Thank you.